Welcome to Lecture 1-4, Robot Potency. A robot must be able to act on its environment. Common acts are in service of locomotion and manipulation, but there are many others, like cleaning, for example, vacuuming, cutting, for example, CNC milling, and delivering material, for example, 3D printing or water jet cutting. As is often the case when deepening our understanding of a device, following the flow of energy through it, a robot in this case, will help us better understand it. We start with where the robot gets its energy and follow this through its application to the environment in an action, as shown in figure 1.5. So we have a source which delivers the power or energy to some sort of storage element on the robot, and that storage delivers power to what we'll call a former, or something that forms the electronic power, which gets then delivered to an actuator, like a motor, which then delivers power to an effector, okay, like a fin or a gripper. And that, in turn, delivers power to an environment. So, this is how the power flows through the robot, and we're going to follow that chain. And we'll start out with energy, where it comes from for the robot, and where it's stored. Actions require energy, which is typically delivered on demand from the electrical grid for stationary robots, typically manipulation arms, of course, in manufacturing environments, and delivered from an onboard battery for mobile robots. Some mobile robots can harvest energy, for example, via solar panels, but the rate of harvest is typically much slower than is required for peak performance. Therefore, mobile robots tend to have energy limitations, and battery technology is crucial for mobile robot development. Box 1.1, Self-driving cars and batteries. Self-driving cars are typically electric and rely on large, rechargeable batteries, typically of the lithium-ion variety. Considerations here include energy storage capacity, vehicle range, power ratings, vehicle power, recharge rate, driver waiting for recharge, self-discharge rate when just chilling, specific energy in, say, an energy unit like joules per a mass unit like kilograms, and the lifespan of the battery. So these are types of things that are very important for self-driving cars, their ability to replace gas-powered cars, and I guess desirability for consumers. Electrical power forming. Before a robot applies power to the environment, it must first transform it into the appropriate form for its actuators, which we'll consider in a moment. The two primary forms of electrical power are direct current, or DC, and alternating current, or AC. Batteries deliver DC power, and the grid delivers AC. Some actuators take DC and others AC power. In mobile robots, due to a reliance on DC battery power and the efficiency cost of DC to AC conversion, DC actuators are preferred. In stationary robots, like those for manipulation, AC power is plentiful, so both AC actuators and DC actuators using AC to DC conversion are used. Further, subforms of DC and AC power can also be identified, as outlined in figure 1.6. So we'll make reference to this figure at the bottom here. These subforms come about because most of the time actuators will need to be delivered variable quantities of power, not just a constant power. For instance, switched DC power, or pulse width modulation, can be used to deliver variable average power to an actuator. By rapidly switching DC power on and off, the actuator average power is varied. This digital electronics technique is usually less expensive than the analog amplifiers required for truly continuously varying DC power. A drawback of switched power is that it introduces significant high-frequency noise, which can negatively impact sensors on the robot. AC power also has subforms. So we've covered DC power over here, continuously varying with analog amplifiers, or switched or PWM style variation of DC power. Over on AC, we have a couple subforms we'll explore here too. Some high-power AC actuators require multiple phases, frequently 3, so 3-phase is the most common. In this case, 3 different signals with proper phase differences must be delivered. Other AC actuators operate at 1 steady-state speed per frequency of AC power. For changing speeds, this frequency must be varied, something achievable with what is called a variable frequency drive, or a VFD. That brings us now to actuation. Now our power is formed correctly for the actuator. Actuation is a robot's transduction of electrical power to the proper energy domain for its corresponding effector, which we'll consider next. Usually, this device is electromechanical. In fact, the paradigmatic actuator is the motor in its 31 flavors. 31 flavors, of course, being the Baskin-Robbins ice cream chain. And I believe that, I'm not sure if there are 2 N's there. They have 31 flavors, or they had 31 flavors, which is lots of flavors. Most motors convert electrical power to rotational mechanical power, but some, called linear motors, convert to translational power. The fundamental mechanism in a motor is the Lorentz force, acting on a wire, surrounded by a magnetic field and through which electrical current is flowing. The varieties of motors are essentially different methods of arranging for this mechanism's unfolding. The following list describes some types of motors important for robotics. DC motors is the first type. They're those that require DC power in its various forms. For example, switched or continuously varying. BDC or brush DC motors have a mechanical contact that reverses current flow. These are inexpensive but are less efficient than other types and require more maintenance due to brush wearing. Permanent magnet DC or PMDC motors are brushed and have a background magnetic field generated by permanent magnets. These are relatively easy to model but require feedback to control. They're also probably the least expensive type that we'll consider here. Wound stator DC motors are brushed and have a background magnetic field provided by an electromagnetic coil. Okay, so that's the wound stator type. Brushless DC motors, or BLDC motors, are actually pretty much an AC motor with complex built-in electronics that allow it to act like a DC motor. These are more expensive and require expensive electronic controllers, but require less maintenance than brushed DC motors, so it's pretty advantageous. More high-end though, higher cost, so it depends on the application if you'd like to use it. Stepper motors are DC motors that usually rotate a predictable amount for each DC pulse applied. The usually qualifier here means that for accurate position control, feedback is still required. These are fine for some position control, but are not great for continuous rotation or high speeds. AC motors are those that require AC power in its various forms. For example, multi-phase. Induction or asynchronous AC motors generate a rotating electromagnetic field that induces current to flow through an electrical loop in the rotor, the part that spins with the shaft. So the rotor is the part that's spinning. You have your motor. This is your rotor that's spinning. My pen here is the rotor. Okay, so, or my pen is maybe the shaft and the rotor, if you will. They spin together. Again, the Lorentz force kicks in. In steady state, there's a difference called slip between the rotation rate of the electromagnetic field and that of the rotor. The speed of these motors is varied by changing the frequency of the AC power with a VFD. These are very common for large load industrial applications. Synchronous AC motors generate a rotating magnetic field on both the stator, the part that doesn't turn, so the stator is connected to the hand part, if we were going to go back to this analogy. The stator, the part that doesn't turn, via electromagnetic coils, and on the rotor via either permanent magnets or DC electromagnets. Since they do not rely on magnetic induction or asynchronous AC motors do rely on induction, the rotor field and stator have the same angular velocity in steady state. In other words, there's no slip with synchronous motors. If the rotor uses an electromagnet, brushes are required with all of that baggage. So that's usually not desirable to bring brushes back in here. These can be more expensive than induction motors, but they can also be driven by a VFD like an induction motor can. Another term frequently encountered here is servo motors, which has two common meanings. The first is simply most any of the motors above of suitable quality for precise feedback control. So a quality motor of pretty much any of the previous types, with the possible exception of stepper motors, which typically are not considered to be servo motors. The second way of understanding the term servo motors, or the second way that it's used, is really a package. A motor, a speed measurement device, usually an encoder, and a feedback controller. Sometimes the controller is included, and other times it is sold separately. So that's sort of the two ways the term servo motors is used, and it's important by context to be able to differentiate between the two. Since the desired effect of the actuator on the effector is frequently not simply rotation in the range of speed and torque of the motor, mechanisms frequently comprise the final stage of the actuator. Mechanisms are, of course, the stuff of mechanical engineers' dreams. Gears, spools, pulleys, linkages, belts, tracks, power screws, etc. So we don't always want just a rotation. A lot of times we want a more complex actuation to happen. And that's where all these mechanisms come in. Affection. I know what most of you think when you hear the word affection, but it also means to affect the robot's environment in this case. Most of the time, this is a mechanical interaction. And interaction it is. Let's not forget Newton's third law here. The robot's structure and, if applicable, base will experience reaction forces. Devices actuators use to yield effects in the environment are called effectors, which have direct interaction with the environment. Common effectors include pretty much all the locomotion devices considered previously, so propellers, fins, wheels, that type of thing. and grippers, claws, feet, wipers, water jets, high-power lasers, sanding pads, and suction cups. Those are just a few examples, but there are all kinds of effectors that we might want our robot to have. And you'll also hear the term end effector, which essentially just means effector. Effector on the end of an arm frequently. So that brings us to an example. Power flow through a solar rover bot. Consider a solar-powered rover bot for exploring the surface of Mars, illustrated below. For the behaviors of A, driving, and B, collecting a soil sample with an arm, trace the flow of power through the robot, and along the way identify energy storage elements, energy transducers, actuators, and effectors. So let's do this together. Here's our nice cartoon of our robot, and we see we've got a solar panel, we've got a robot arm, we've got wheels to get around. Okay, so let's look at part A, driving. Okay, so for driving, we have the power flow is going to start for both of these cases with the source of the energy, which is solar, right? So solar energy will come in through the solar panel. So it'll go solar panel, and it'll go from there into a battery. We must have a battery on here because we aren't going to have enough power or energy per unit time coming in from the solar array to do high power demand things instantaneously. So we can't flow that power directly into our actuators. We need it to be stored first, so we can accumulate it in the battery. And from the battery, this thing, so it's going to go into these wheels. So we have to think about how that power should be delivered to the wheels. Let's say that the actuators for the wheels are permanent magnet DC motors. Okay, so permanent magnet DC motors could be driven in variable speeds. In driving, you're going to need to have variable speeds, of course, for these motors. So we're going to actuate these wheels with permanent magnet DC motors. We could use a switched supply here, or we could use an analog amplifier. Kind of depends on the situation. Presumably, we would spare no cost because this is a rover on Mars, so our budget is large for this project. But we also are concerned about things like the complexity of the electronics involved. So if a switched source, using PWM, might not be as reliable in some cases. Probably would be just fine, but there are different things you could weigh here between a switched source and a continuous amplifier. Let's say we went with a continuous amplifier, okay? All right, then the power is going to go into, we already decided it was going to be a PM DC motor, or several of them, maybe one for each wheel. Probably want each of the wheels to operate independently. Now, this is, of course, so solar panel is a type of transducer. We're supposed to be recognizing transducers along the way. It transduces the radiative energy from the sun, light energy from the sun, into an electrical energy, and the battery stores it. So that's an energy storage element. The continuous amplifier, it actually is going to just add power to a small signal that comes from a controller, probably, to give it some of the power from the battery. So it doesn't really do much besides maybe change the form of the power. And PMDC here, the DC motor, is going to, of course, be a transducer that changes electronic energy into rotational mechanical energy. Now, there is probably, if we're going to use a permanent magnet DC motor, these things don't tend to have a relatively low torque and are really efficient at only a sort of small range of speeds. So most likely we're going to want to gear this. Gears. So for things like increasing our low speed torque and our high speed torque for that matter, and allowing it to be more efficient, because of course efficiency is going to matter on a mobile robot like this. Limited amount of ability to harvest energy. So some gears. So this will be a nice mechanism here. And then finally we go into the wheels, which are of course the effectors. So source, storage, this we called former, or something that forms the electronic power. The DC motor is a type of actuator, but really this motor and the gears together are the actuator in this case. And wheels, which are the effector or effectors. Great. So that was part A. For part B, we are going to be collecting a soil sample with the robotic arm here. So let's follow things for the sample. Follow the chain of energy flow. Again, it's going to start, has to, with the solar panel. It's the only thing we know, at least in terms of where the energy is going to come from. So solar panel, and it's going to go into the battery again, which has to supply power for driving, but it also supplies power to the robotic arm. So although you probably wouldn't want to move that arm around when you're driving, it's probably also not going to be possible in terms of power demands. So battery is going to supply power to something that has to transform this energy or form this energy, this electronic energy, to move this robot arm. The end effector here is going to be this gripper, or maybe it's a scoop. I'm not sure how we would best want to have this end effector work. Potentially it would be a gripper and it would hold a vial, for instance. Something like that. A scoop would work too, but then the question is, once you have it in the scoop, what do you do with it? So the gripper would hold, say, a vial, scoop up some dirt, place it in the robot somewhere to carry. So we have a gripper end effector, or effector here, and we need to know how we're going to make that gripper interact with the environment. So we're going to do that through manipulating this robot arm here. And the arm has, as different aspects of it, motors at the joints, of course, and we have these mechanisms, because the joints are not just simple motors. They also potentially can turn in one direction or maybe multiple directions. Maybe there's a swivel, socket joint, different possibilities here. So mechanisms will also come into play. and then the lengths of these arms. So linkages come in, mechanisms come in when you have an arm. So motors for an arm like this. DC motors are good choices frequently. It depends on the size here. We didn't really talk about the size, but this is, typical Rovers are relatively small. Maybe we would choose something like a brushless DC motor. And we would want to choose a brushless DC motor in part because there would be very little maintenance required for a brushless DC motor. There are always trade-offs in the design though, so a brushless DC motor, a permanent magnet DC motor, a wound stator DC motor, even a stepper motor might be good here. An asynchronous motor, or an AC motor that's asynchronous or synchronous, induction or synchronous, would be a bad choice because we only have DC power on board. The battery would have to have its power converted into AC power to drive something like that. So we would prefer to use a DC motor like a brushless DC motor, or another variety of DC motor. So say we're going to go with a brushless DC motor. The electronics there are rather complex, but we have to have a brushless DC driver, let's call it. Motor drivers are something that the circuits are called. And that's going to go into our brushless DC motors. So we've got probably multiple drivers, independent motors, and that is going to go into this sort of arm mechanism, right? So I'll just call it arm to encompass the joints and the lengths of arm as well. And then finally the arm is going to transfer that energy into the gripper. Okay, and then the gripper interacts with the environment. So this is an example of how power flows through a robot. And as we followed that power flow, we were able to deepen our understanding about the different aspects of how a robot is potent in the world, can act in the world. So that's the lecture on robot potency. Take care.